On Monday in class, I put up this graph here, this image, and I asked, "What is it?" And it actually took a while to get people to begin to work out what it was. So I want to go through this in detail because this ought to make sense to you guys. So the first thing that you do when I ask, "What is this?" is be completely descriptive. It's a graph. The x-axis is wave numbers in inverse centimeters, and they're sort of small. They go from 0 to a few hundred. The y-axis is something called sigma, and it's got units of area, square centimeters, and they're also small because they're multiplied by 10 to the 20, and there's about 1,000 of them or so. So there's something like 10 to the minus 17 square centimeters, and you might remember that sigma is what we use to represent a cross-sectional area for a molecule. So I then again work through Beer's law and the fact that if we put one molecule inside of a column of length L, it's going to have a physical size, let's say in one dimension, roughly an angstrom, which is about 10 to the minus 8 centimeters. And so its area is going to be very roughly that physical size squared, or about 10 to the minus 16 square centimeters. So the physical size of the molecule is maybe 10 times larger than the size scale on the y-axis here, which goes up to about 10 to the minus 17 square centimeters. So that tells us that we're dealing with some sort of interaction with an individual molecule, and this value sigma indeed is the cross-sectional area that the molecule presents to a photon, and a photon of wave number of color equal to the wave number shown on the x-axis. So that's why we're dealing with Beer's law here. Now, to get the total area that all of the molecules in this column present to that photon as it tries to get through the column, we have to take the cross-sectional area of an individual molecule, multiply it by the concentration of all the molecules in this absorption cell, and then multiply that by the length of the cell itself. So concentration times length is molecules per area, which you can think of as molecules per unit surface area of the opening in the end of the tube that we're trying to shine the light through, and then the cross-section itself has units of area per molecule. So all told, this gives us the cross-sectional area of all the molecules per unit area of the opening in the tube, and that's what we want to know. So that's how tightly, how much area we can cover up the tube with. So if that total area is less than 1, if we have less than a square centimeter of molecular surface area per square centimeter of opening in the tube, obviously some light's going to get through. But even if it's exactly 1, we'd only obscure all of the light if the molecules could exactly perfectly line up with one another like a whole group in a photograph. And that doesn't happen. The molecules are wandering around randomly, and they overlap with each other a lot. And so that's essentially why we take this thing, which we call the optical depth, and it winds up in this exponential form called Beer's law. So that's the effect that molecules are going to have on the absorption. So then I started with the question of what is this? What's happening? And we finished the description here that we're clearly looking at the energy of something, and because we're clearly looking at something that has to do with the interaction of molecules in some way or another with light. It's a reasonable premise, reasonable supposition that the x-axis wave numbers here are the color of light, are the wave numbers of photons that are interacting with some of these molecules with this cross-sectional area shown on the y-axis. And since the energies that we're looking at are some tens of wave numbers in between these lines here, that's an energy that's characteristic of rotation, and so we'll make the jump, make the leap, which is correct, that we're looking at a situation where the energy transition is rotational. So we're changing the amount of energy in rotation of the molecule, and our quantum representation of rotation in a molecule in units of wave numbers is this expression the B value times a quantum number L times L plus 1, where L can be 0, 1, 2, 3, etc., the principal quantum number L associated with total angular momentum and thus energy. Remember, there's also a Z angular momentum quantum number M sub Z that can go anywhere from negative L all the way up to plus L, but that doesn't have anything to do with the total energy there. So that's the energy of the photons. And then in order for this thing to increase in energy, that principal quantum number L must go up. So that's the way we express that. If the energy goes up, the quantum number has to go up. It turns out the quantum number can't just go up by anything. There's this thing called a selection rule, and the change in that principal quantum number has to be exactly plus 1. And that's it. So that makes it quite a lot easier. We'll go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, etc. The reason for this, by the way, if you think back to our hero, the photon, you might remember that our hero, the photon, is a thing called spin angular momentum, and a photon is a spin of 1. So the spin angular momentum of the photon is 1 unit of angular momentum, and that's got to be conserved. The angular momentum of the photon can't just go poof when it interacts with a molecule. So the photon's bringing energy to the table, and that energy is going to make the total energy level of the system go up. So the L value has to go up, but the photon's only bringing 1 unit of angular momentum to the table, and so it can only make the angular momentum quantum number go up by 1. That's all it can do. It actually turns out that the Z component of the angular momentum has to change as well, or it might change, and it can change by plus 1, 0, or minus 1. So I can bring that photon angular momentum into the system and at basically 3 different angles with respect to the angle of the molecular angular momentum, which will come up just a little bit later, but it's not that big a deal. The big deal here is that I can't do anything more than bring in 1 extra unit of angular momentum, and so delta L has to be plus 1. So I can't stress this enough, but it's super important that when we do spectroscopy and a photon is absorbed by a system, the energy goes up, and so the energy level of the system goes from an initial value to a final value. So the energy of that photon is equal to the change in energy of the system. So the delta new rotation, the delta wave numbers of the rotational system, the formula up on top, is equal to the energy of the photon. And the change in the rotational energy of the system is given by an initial quantum number, well, a final quantum number L plus 1 minus an initial quantum number L for a change in L of plus 1. So that's going to give us a B value times L plus 1 times L plus 2 for the final quantum number minus L times L plus 1 for the initial quantum number. It's minus because we have a difference, higher minus lower. We can easily factor that out. The L plus 1's come out. We get B times L plus 1. And then the residue here, there's an L plus 2 and a minus L. Well, those L's cancel out, and all we're left with is 2B times L plus 1. And now L plus 1 is actually just the final L. So it makes a little more sense to write this as 2B times the final L as the most compact way of representing the wave numbers of the photons that we expect to find here. And that final L can go from 1, 2, 3, 4, etc. So you can't have a final L of 0 because L has to have gone up by 1. So the very first transition is 0 to 1 that's allowed. So that's where we expect to find the energies of the photons, very precisely at these values, 2B times the times 1, times 2, times 3, etc. So if we look at this final L as we look across these vertical lines here that are the absorption spectrum, the first one is a final quantum number of 1, the second one's 2, the third is 3, the fourth is 4. So this highest line, 4 here, is equal to this molecule going from a state that's defined by quantum number L equals 3, so that level 3, up to level 4. And that's the strongest transition in this case here. So the spacings are 2B. So the interval between those lines, because 2B times L, and so for each L I add another 2B to this line position, so that interval is 2B. And that interval is just a scooch over 40 wave numbers, and so our B value is just about 20 wave numbers. Well, what's the B value? It's given by the formula 16.87 divided by the moment of inertia, and you really ought to remember that number. You can write it down on your sheet, you can look it up, or you just know it, and you'll get it faster when you're working on the exam. So the B value is 16.87 over the moment of inertia. The B value in wave numbers in the moment of inertia in AMU angstrom squared. In this case, that's about 20 wave numbers. So we can easily solve that for the moment of inertia. It's about 16.87 divided by 20 gives 0.8 AMU angstrom squared. And now, since bonds are typically about an angstrom or so, that means that we're looking at a reduced mass, which is mu r squared, remember. The reduced mass is something around an atomic mass unit. And that means that this system has to have a hydrogen. It's a hydrogen spinning around something, XH. And actually it turns out that's exactly what it is, HF. So that's how you go about the business of using a spectrum and looking and analyzing a spectrum to figure out what a molecule is, or at least roughly what a molecule is. And in fact, given that the B values are known, you can use the spectroscopy to precisely identify a molecule eventually, but you can figure out kind of roughly what it must be just by looking at it.